So let's go ahead and work some of these problems. A lot of the stuff you should be able to do, but as we get into manipulating the currents and stuff like that, that might be a little bit of trouble. So this first one is all in series. So all you have to do is add up the resistances. So 10 plus 20 plus 30. Our equivalent resistance is 60 ohms. So if we have 60 ohms, our total current is just going to be 6 divided by 60. So 0.1 amps, right? 6 volts divided by 60 ohms. So that's going to give us 0.1 amps, right? Because V equals IR. So if I want the current, I just take voltage divided by the equivalent resistance. This is in series, so the current will be the same everywhere. Right? Then our voltage, we have 6 volts. So we have to spend that 6 volts all eventually once we get around here, but they don't each get 6 volts. So I can do that by using this V equals IR. So for this first one, we'll do 0.1 times 30. So that's 3 volts. 0.1 times 20. So that's 2 volts. 0.1 times 10. That's 1 volt. And then, hey, guess what? 1 plus 2 plus 3 equals 6 volts. It's magic math, right? So that's everything on that one. This one, kind of similar stuff here, except this one's in parallel. I can't add up the resistances. I add up the inverse of the resistances. So 1 divided by 10 plus 1 divided by 20 plus 1 divided by 30. And that gives us 0.183. I inverse that, right? And that gives us 5.4. So it is less than any one individual path, which makes sense because, you know, it's like 3 paths for a river kind of thing. So I do 6 divided by 5.45, and that gives us 1.1 for our current. Here, we got to say the current was the same everywhere. Here, the current is not the same everywhere. Here, the current is going to split on each of those. But the voltage has to get spent before it comes around. So if you watch the voltage, right, this is where that loop rule kind of starts to come in handy. I have 6 volts to spend by the time I come around here. Well, that means that this resistor 1 has to get 6 volts. See here, you had to spend 6 volts, but you went through all 3 resistors before you spent that 6 volts. You can kind of think of voltage a little bit like a currency here, right? So this one's going to get 6 volts. This one's also going to get 6 volts. And this one's also going to get 6 volts. So they'll each get 6 volts. So I can do 6 divided by 10 for 0.6, 6 divided by 20 for 0.3, and 6 divided by 30 for 0.2, and 0.6 plus 0.3 plus 0.2 is going to give us 1.1. Look at that. It's like magic, right? See, look at that. You can even double check on your calculator. 1.1 is the total, whether we did it this way or this way, right? So we look at one that's a little bit more complicated yet, right? Now here, when I go to do my loops, right? So I'm going to spend some of my voltage, then my current's going to split. So I need to do that equivalent resistor thing. So I'm going to turn these two into an equivalent resistor of 1 divided by 20 plus 1 divided by 30. And that equivalent resistor is, and inverse that, is 12. So my total resistance, or my equivalent resistance, is going to be 22, which means my total current is going to be 6 over 22. So 0.27 amps is my total current, right? So I found that equivalent resistor. I added that up and got the equivalent resistance of the whole thing. Did V over R to get my current, just like I did up here, right? So then the current through each one of them, well, the current, just follow the path. Well, this one's going to have to get all of the current. So the top one will get the 0.27 amps. But then my current's going to split, and some's going to go each direction there. Right? Now, there's some complicated math we can do there, but I would just as soon go ahead and fill in the whole table. I know 2 of the 3 things here. I know my resistance and I know my current. So if I multiply my current by 10, that'll give me my voltage, right? Because again, V equals IR. Get to know that relationship real well. So 2.7 here. That means I've spent 2.7, so I have 3.3 left. Both of these are going to get that 3.3. And hey, look, now I've got 2 out of 3 again. So 3.3 divided by 20 is going to give me 0.165. 3.3 divided by 30 is going to give me 0.11. If I add up the 0.165 and the 0.11, right? So plus 0.165 That gives me my 0.27. That's my total current, right? So my current 0.27 goes here, and then it splits. So you can kind of think about voltage like currency, and current is like the flow. So you have to, if it splits, it still has to all be accounted for, kind of thing, right? So now we've got a few where they're just asking us some specific spots. So I see my 12 volts here. That 12 volts has to get spent before it comes around here. So I don't have to worry about all this. None of this matters for this particular current right here. For this particular current right here, all I have to do is 12 volts divided by 6 ohms. That current is 2. Okay. I could do these other ones. This current right here is 1. This current right here, who cares though? They only ask us for that one right there. They might ask us for others later. If you have not already, I would try and work through as many of these as you can, so that you can start to do these on your own, right? This is normally a thing I give students, and y'all work in like pairs and groups of 3, and you're able to work through pretty well. Oh, so this one is based off, 6 is based off of this one right here. What is the equivalent resistance of the circuit shown? So this is in parallel. So I would go 1 divided by 6 plus 1 divided by 12 plus 1 divided by 36 plus 1 divided by 18. Inverse that. The equivalent resistance is 3 ohms. What is the current? We already did that because we don't need this whole thing for that. We would just do that current as 2 amps. Right? Go ahead and try some more of those for the rest of today. I will maybe post a video tomorrow with a few more of the answers. You've got the answers back here, right? But do it the right way where you try and figure those out on your own. You've got to have some self-discipline and all that with this, right? Because I'm not here to kind of do as much of the back and forth as we normally do. But try some more of that. We'll tinker with that a little bit more tomorrow, and we should start to where we're getting kind of good at these more complicated circuits.